episode. Today we're going to be talking about one of the best scientists of all time. He lived in the 17th century. His name is none other than Sir Isaac Newton. Now he is the best, if he's one of the best, if not the best scientist of all time. His three laws of motion I will get into his three laws of motion, but I have to tell you what made him do this. In the 17th century, in the 1660s, he was an average student at Cambridge. So he started reading the great works of mathematics, but through them he was drawn away from civic law into the laws of physics. So this is how he formulated his first law. But before he had the chance, the university was closed due to an outbreak of plague, whatever you want to call it. So here, borrowing Galileo's principle of inertia, he formulated his first law. It says that object to rest, stay at rest, object moving, stay moving. So this is hard to appreciate in our own experience, but if we throw a hockey puck, it skips along the ice, but eventually slows due to friction with the ice. Now the nearest we might get to no friction is in space, but even here, there is still forces such as gravity at work. Oh, did I mess up your little brains? Of course I did, because you never knew that gravity in space you're actually experiencing 90% of the gravity actually you're only experiencing 10% less gravity in space than here. So I'm sorry I messed up your brains. Anyway, the second law is acceleration. So here we have to say that the acceleration is proportional to the mass times its increase in speed per unit time. For example, if you wanted to accelerate your car from 0 to 100 kilometers an hour, which is 0 to 62 miles per hour, in 1 minute would take the car's mass times its increase in speed per unit time. Next, so the second law expressed algebraically is force equals mass times acceleration. Key fact of the day. Okay, maybe not. This is not the key fact of the day. So anyway, turning this definition around, we will see that it says that the second law expressed in a different way says that force is equal to the force per unit mass. For a constant acceleration, force per unit mass is also unchanged. Action equals reaction. Key fact of the day. Key fact of the day is that we exert if I throw a ball down, it will bounce back up to me, right? That's because it exerts a small downward force on the Earth. But since Earth is so much more massive than we are, it barely even shows. So that would mean we can't see it at all. Even if we look so closely, we can't. We can't just see it exert the force. Don't forget that was the key fact of the day. Every time you throw a ball down, there's an equal and an opposite reaction. So the ball exerting the force is the action. And the reaction is the floor bouncing up and making it bounce back up to you. So here we go. But a marksman feels the kick of the rifle as he shoots. The victim of a shooting in crime films often gets propelled backwards from the bullets. But this is misleading. If the force were really so great, the shooter would also be hurled back by the recoil of his gun. With these three laws plus gravity, Newton could have confidently climbed aboard a fast motorbike and sped up onto the vertical wall of death. The first law says that the cycle and its rider would want to keep riding at the same speed in a certain direction. But to keep the cycle moving in a circle, a confining force needs to be laid down from the wheels through the wheels to the track. The third law then explains the pressure exerted by the wheels to the track, the tires to the track basically. So it is that this pressure that glues the bike to an inclined wall. And if the bike goes fast enough, it can even ride on a vertical wall. Even today, in the 21st century, a lot of centuries before, 4 centuries before Newton formulated his 3 laws, even now, even today, all you need is Newton's 3 laws of motion to explain pretty much everything. Falling acorns, balls fired from a cannon, bullets shot from a gun, which I mentioned earlier. Second key fact of the day, where these laws do not hold, however, is in when things are moving close to the speed of light, or maybe things moving faster than the speed of light, like our universe, which is expanding forever and ever and ever and ever and ever. But it is in these, or with very small masses, it is in these extremes that Einstein's relativity and the science of quantum mechanics completely take over. I hope you enjoyed this episode about my best inspiration. I hope you enjoyed my best episode yet. This was Captain Adam. Bye.